Chapter 1, Relations and Functions. In daily life, we have so many relations, like the relation of son, the relation of father, the relation of brother, the relation of mother, etc. In math also, we have relations like 14 is a multiple of 7, 3 is the factor of 9, 3 and 5 are co-prime to each other. So here we have to discuss following topics. First one is we introduce the relation. In earlier classes we have discussed relation and function and its definition. Here we will discuss following topics. First one is types of relations. Second one, types of functions. And third one is composition of functions. And invertible function. Here also binary operation is given, but according to the syllabus, binary operation is not to be studied. So let us start with definition of relation. Relation. It is the subset of the Cartesian product of any two sets. For example, on the set A, the relation R, the set of all ordered pairs such that A is the multiple of B can be enlisted as Eight is the multiple of 2, 6 is the multiple of 2, 6 is the multiple of 3. So this is the relation of multiple in the set A. It is the subset of Cartesian product A cross A, which is a subset of A cross A. Now we are going to discuss types of relations. So first one is empty relation. A relation R in a set A is called empty relation if no element of A is related to any element of A. That is, phi is a subset of R is equal to phi is a subset of A cross A. For example, A is equal to the set of all students in a boys school. Then the relation R in A given by R is equal to the set of all ordered pairs such that A is sister of B. We know that set A is the set of all students in a boys school, so no one is girl there. But here we define a relation where A is sister of B. So it is impossible for this set that a student may become the sister of another student. Let us see next type of relation. This is universal relation. A relation R in a set A is called universal relation if each element of A is related to every element of A. That is, R is equal to A cross A. For example, for the set of all students in a school, then the relation R in A given by R is equal to the set of all ordered pairs AB such that the difference between the heights of A and B is less than 3 meter. As we know that 3 meter is very large distance, and we can say that there is no two students in the school where the difference in their heights is equal to 3 or more than 3. So if we take this relation between two students, then we can say all elements of the set A are related to each other. Let us take next type of definition. This is equivalence relation. A relation R in a set A is called an equivalence relation if R is first reflexive, second symmetric, and transitive. Let us know about reflexive, symmetric, and transitive. So this is D. A relation R in a set A is called reflexive if A belongs to R for every A belongs to A. Second, symmetric if A1, A2 belongs to R im- implies that A2, A1 belongs to R for all A1, A2 in A. Now third, transitive if A1, A2 belongs to R and A2, A3 belongs to R implies that A1, A3 belongs to R for all A1, A2, A3 belong to A. Let us do a question. Question number 1. Relation R in the set A of human beings in the set in a town at a particular time given by A R the set of all ordered pairs xy such that x and y live in the same locality. B R the set of all xy such that x is exactly 7 centimeter taller than y. C R xy such that x is wife of y. Determine whether the above said relations are reflexive, symmetric, and transitive. So first here is we have to decide reflexivity in the relation. Here relation R is the set of all ordered pairs xy such that x and y live in the same locality. So reflexivity. We can say X and X belongs to R as X lives in the same locality. Symmetry. X, Y belongs to R imply that X and Y live in the same locality, implies that Y and X live in the same locality. This implies that Yx belongs to R. Transitivity. Let Z belongs to the set A of human beings in the town. Now XY belongs to R and YZ belongs to R implies that X and Y live in the same locality and Y and Z live in the same locality. This implies that X and Z live in the same locality. This implies that XZ belongs to R. Hence, R is reflexive. You may see that according to the definition, if for every element in the set A, each element is related to itself, then it is reflexive. That exists here, so R is reflexive. If A1, A2 belongs to R implies that A2, A1 belongs to R, then the relation becomes symmetric. And for transitivity, if XY belongs to R and YZ belongs to R, then XZ belongs to R, then R becomes transitive. Hence, R is reflexive, symmetric, and transitive. So this relation R is also equivalence relation. Let us see next one. Here next question was X is exactly 7 cm taller than Y. Reflexivity. Here X and Y are two persons. X does not belong to R as no human being can be 7 centimeter more than oneself. So R is not reflexive. Now symmetry. X, Y belongs to R implies that X is 7 centimeter taller than Y. This does not imply that Y is equal to X plus 7. So Yx does not related to R. So R is not symmetric. Now transitivity. Let us take an element Z in R, Z in A. XY belongs to R and YZ belongs to R implies that X is equal to Y plus 7 and Y is equal to z plus 7. From here we can say, if we put y is equal to z plus 7, we have x is equal to z plus 14. That's why we can say that this does not imply x is equal to z plus 7. So xz does not belongs to R. So R is not transitive. Hence, R is neither reflexive nor symmetric, neither reflexive nor symmetric, nor transitive. Let us see the third question. Third one is here reflexivity. Here the given relation is the set of all ordered pairs x y such that x is wife of y. X is wife of y. So for reflexivity, we can say that xx cannot belongs to R, as a human being, x is human being, x can't be wife of oneself. So R is not reflexive. Now symmetry. xy belongs to R implies that x is wife of y. X is wife of y. This does not imply y is wife of x. So yx does not belongs to R. So R is not symmetric. Now transitivity. Let z belongs to A. xy belongs to R and yz belongs to R implies that x is wife of y. Then y is husband, y is male. This does not imply y is wife of z. So there is no z for which y male becomes wife. Hence it is transitive because yz does not exist. Hence R is neither reflexive nor symmetric but transitive. Here it is worth mentioning that uh, if an ordered pair exists in R, suppose xy belongs to R and yz does not exist in R, then this relation is transitive. Question number 2. So that the relation are in the set of real numbers in the set of real numbers defined as the set of all ordered pairs AB such that B square is neither reflexive nor symmetric nor transitive. Solution. Here given set is the set of real numbers and the relation is R such that A is less than B square. First one, solution. We have to show it is neither reflexive. So we have to create a counter example. So for A is equal to 1 by 2, A does not belong to R as 1 by 2 is not less than or equal to 1 by 2A square. Symmetry. Symmetry. For A is equal to 2, B is equal to 5. 5 belongs to R as 2 is less than or equal to 5 square. But 5 2 does not belongs to R as 5 is not less than or equal to 2 square. Transitivity. For A is equal to 2, B is equal to 5, C is equal to 26. 5 belongs to R and 26 belongs to R as 2 is less than or equal to 5 square and 5 is less than or equal to 26 square. Here we have to think example which is counter for this. So this does not true. So we have to take A is equal to, suppose we take A is equal to 2, B is equal to -3 and C is equal to -1. Then we see that 2 minus 3 belongs to R and -3 -1 belongs to R as 2 is less than or equal to -3 square. -3 is less than or equal to -1 square. But 2 minus 1 does not belong to R as 2 is not less than or equal to -1 square. So here AB belongs to R and BC belongs to R does not imply that AC belongs to R. Hence R is neither reflexive nor symmetric nor transitive. For showing this relation reflexive, we should take a number between 0 and 1. For symmetric, we have to take A and B such that B will be more than a square of A. For example, if we take A3, then we should take b as more than 3 square, that is 10. Then you can easily show 3 5 3 10 belongs to R as 3 is less than or equal to 10 square, but 10 3 does not belongs to R as 10 is not less than or equal to 3 square. For transitivity, we have to take A as positive, negative. Here we can take negative or positive also. We can take here 1. Then also 2 is less than minus 3 whole square. Minus 3 is less than 1 whole square. But 2 is not less than 2 is not less than minus 1 whole square or 1 whole square. So we have to think and we have to take positive, negative or positive numbers here. We have to produce counter examples so that it become not, it does not become transitive. Now question number 3. Check whether the relation R in R, that is set of real numbers defined by R is equal to the set of all ordered pairs AB such that A is less than or equal to BQ is reflexive, symmetric or transitive. Solution. Reflexivity. Here the given set is set of real numbers and the relation is A is less than or equal to BQ. So if we take A is equal to 1 by 2, then we see that 1 by 2 is less than or equal to 1 by 2 whole cube, which is equal to 1 by 8, is not true. So R is not reflexive. Now take symmetry. If we take A is equal to 2, B is equal to A is equal to minus 2, B is equal to 3, then we see that minus 2 is less than or equal to 3q, but 3 is not less than or equal to minus 2 whole cube. So we have to think more and we have to select a counter example where the relation does not exist. So we can say that R is not symmetry. Now let us see transitivity. For A, here we have to remember the example B 3 by 2, C 6 by 5. We may also take 7 by 5. This is a special type of example. Then we see that 3 is less than or equal to 3 by 2 whole cube. 3 by 2 whole cube is 1.5 whole cube, and which is equal to, here we can see that 3 is less than or equal to 3 by 2 whole cube, that is 1.5 whole cube. Here we have 3.375. 3 by 2, which is 1.5, is less than or equal to 6 by 5 whole cube, means 1.2 whole cube is equal to 1.728. But you can see that 3 is not less than or equal to 6 by 5 whole cube, as you know that this is 1.728. You may also take 7 by 5 in place of C and you get the same result. So you have C, R is not reflexive, R is not symmetric, here R is not transitive. Hence R is neither reflexive nor symmetric nor transitive. Now let us define equivalence class. So given an arbitrary equivalence relation R in an arbitrary set X, R divides X into mutually disjoint subsets AI called partitions or subdivisions of X, satisfying first all elements of AI are related to each other for all I. Second, no element of AI is related to any element of AJ where I is different from J. Third one is union of AJs, union of all partitions, all subsets is X, and intersection of AI and AJ is equal to phi. Then the subsets AI are called equivalence classes. Let us understand it pictorially. Suppose you have this a set X, and on X there is an equivalence relation R. Then R divides this X into mutually disjoint subset. This is our X. You can see that these subsets are mutually disjoint, and here it is also said that all elements of A1 is related to each other. No element of A1 is related to any element of A2 or A3. Union of all AI means union of A1, A2, A3 and so many are the set X. Suppose this is 4. And you can see intersection of any two partition is 5. Then these subsets are called equivalence classes. Let us see an example. So here the question is, so that the relation R in the set A 1, 2, 3, 4, 5 given by R, the set of all ordered pairs AB such that mod of A minus B is even is an equivalence relation, so that all elements of 1, 3, 5 are related to each other and all elements of 2, 4 are related to each other, but no element of 1, 3, 5 is related to any element of 2, 4. See, you can say that these two sets 1, 3, 5 which are subsets of this set A and 2, 4 are partition of this set A because the relation is equivalence, and we can show that these two sets elements are not related to each other, and and elements of this set are related to each other. Elements of this set are related to each other, but no element of this set is related to the element of this set. So these two sets satisfy the condition for equivalence classes, so they are equivalence classes. Now let us show. So we have to show that the given relation on the given set is reflexive, because we have to show that we have to show that the given relation is equivalence. So we have to show that the relation is reflexive, symmetric, and transitive. Here we take A belongs to R. This implies that mod A minus A is even, which is equal to 0 is even. This is true. Now take symmetry. Here we take AB belongs to R. Then we have to show that BA belongs to R. This implies that mod A minus B is even according to the relation. This implies that mod B minus A is even. This is also true. Suppose we take 4, 2. Then 4 minus 2 mod 2 is even. If we take 2 minus 4, then mod minus 2 is 2 is also even. So we can say that BA belongs to R. Now transitivity. Here AB, let C belongs to A, right? AB belongs to R and BC belongs to R implies that mod of A minus B is even and mod of B minus C is even. Then can we write A minus B plus B minus C within modulus even? Yes. Suppose here we have 2, here we have minus 4, then we have 2 plus minus 4 means minus 2 is even. So that property can be applied. This implies that modulus of A minus B plus B minus C is even. This implies that mod A minus C is even. This implies that AC belongs to R. Thus we have shown if AB belongs to R and BC belongs to R, then AC belongs to R. So R is an equivalence relation. Thus R is reflexive, symmetric, and transitive. Hence it is equivalence. Now we have to show second part that all elements of 135 are related to each other. For elements of 135, clearly for its any two elements A comma B, we have for any two elements A comma B we have mod A minus B is even. Suppose you take A1 B5, then mod 1 minus 5 is 4, which is even. 3 5, then 3 minus 5 mod, so 2 is even. 1 3 2 is even. Also for elements of 2 4, clearly for its two elements AB, we have mod A minus B is even. Now for an element of 135 and for element of 135 and other element from 2 4. Now for an element of 1 3 5 and other element from 2 4, clearly we have modulus of a minus b is not even. You can check if you take a1 b2 then 1 minus 2 mod 1 is not even, 3 minus 2 you can, so 1 is not even, 5 minus 2 is 3 is not even, so no element of this is related to any element of this set. Thus this set and this set satisfy all the conditions for being equivalence classes, and whenever a relation is equivalence relation on an arbitrary set X, then the set produces equivalence classes. Hence, it is shown that